All right, so let's take a look at this problem right here, and we're going to take a look. Here's the horizontal pulley. Here we have the Atwood machine, and off to the side we have the incline. And what I want to do is show you how these are kind of the same problem over and over with respect to Newton's second law. We're going to go with this idea. The sum of the forces is equal to the mass times the acceleration. All right, so let's see what we have going on. We're going to do this without friction first. So we have this horizontal pulley here. Let's call this mass 1. We'll call this one mass 2. And there's going to be a force. There's only one force that's going to be driving this whole system along, and that's going to be the force of gravity on the second box, which is going to be m2g, and there is no other force. If there was a frictional force on box 1 between the surface here, it would be going this way, and we would have to include that at some point. But let's look at this right now without that force of friction. So we know that that's going to be our force, the weight of box 2, and that's going to be equal to the mass of the entire system. So that's going to be m1 plus m2 times the acceleration. So if we had numbers and we wanted to find the acceleration, we would just add these two together, and that would give us our formula, or give us our actual acceleration here. If we wanted to solve this for the acceleration, we could say the force on the system divided by the total mass of the system. Don't forget that there is, this is the easy way to do this. There is the substitution version that we're not going to get into here. And let's take a look at the Atwood machine and compare it. So this is mass 1 and mass 2. Just to be fun, we'll make this direction positive and this direction negative, because things that rotate in this counterclockwise direction, that's a positive rotation. So now I know these are both pulling down, but with respect to the pulley, they are pulling in opposite directions. So we're going to say that the weight on box 1 is positive and the weight of box 2 will be negative. And this is different than the horizontal pulley in that there is now a new force in here, which is the weight of box 1. And so let's set this up. What would this look like? Well, we would just, using the same idea, sum of the forces is equal to mass times acceleration. We know that there's going to be two forces, the weight on box 1 and the weight on box 2, so we need to add those together. Let me make that negative. Make sure you make that negative or that won't work out for you. And now it's the same thing. We just add up the mass of the entire system. We're going to assume that the mass of the pulley is negligible and the mass of the cable is negligible. And there's our acceleration. So if we had numbers here, we would just put them in and that would give us our acceleration. If you wanted to factor out the acceleration due to gravity, you could, but it doesn't affect anything. All right, so there we are. That would give us our acceleration here. Now, what about the incline? Well, okay, let's take a look. So we'll make this box 1 again. Here's box 2. I'm going to make this force going down this direction positive, and the weight on box 2 will be negative. So let's see here. We're going to have negative the weight of box 2, and then here we're going to have the force pulling on box 1. We do need an angle for this incline, so it would have some angle theta, and we, hopefully you remember from before, that the mass times the acceleration due to gravity times the sine of the angle will give us the component of force that is pulling down the incline. Okay, so what? Well, when we look here, let's add up our forces. So we're going to have, same thing, sum of the forces will equal the mass times acceleration. Newton said so. And we're going to take the mass of the first box times the acceleration. It's the same formula as the Atwood machine. The only thing that you do is you stick in the sine of theta. It's the only difference. Until you bring in friction. When you bring in friction, that becomes a whole nother thing. But you would have to know what direction the box was sliding in order to even insert friction. So let's take a look here. And there's our sum of the forces. We now have to have the mass of the entire system, mass 1 plus mass 2 times the acceleration. If we wanted to solve for the acceleration, divide both sides by the mass of the entire system. And there you go. That would pretty much take care of that. And if you look at all three of these, let me zoom out a tad, it's really just kind of a progression. Every one of these has its own little nuance here when you add it in here. When we take a look at the horizontal pulley, if we had friction acting on this box, so let's say there was a force of friction here, we could then say we would have to add that in here. So let's say if we, with friction, we could bring that in. That would be, that's going to be, we made this positive, so in this case it would be negative. So we have a negative force of friction. And we're just assigning directions here. You could have opposite signs if you wanted to. It's going to be that's pretty much it. We're just going to include the normal force on box 1 and the coefficient. There's some information you would need to have, or they would just need to give you what the force of kinetic friction is. But let's just say it's Fn times the coefficient. That will give us friction. And that would go there. If you looked at the incline, and we wanted to look at friction here, we would need to remember, one, that the normal force between the surface here, box, I'm going to draw it coming out of the top, but it's really between the bottom of the box and the surface of the incline, is going to be mg cosine of theta. So where does that come into this formula here? Let me draw a line here and say with friction. I'm going to make the assumption that it is sliding down this direction. If that is the case, then the force of friction would be going this direction. If the mass of one was great enough to make the object slide down the incline, then friction would be going the other direction. You would have to assign your positive and negative values appropriately, but we're going to assume that it's mass 2 pulling mass 1 up the incline, and so let's bring in friction. So we would have the force of friction plus m1g sine of theta minus the weight of box 2, mass of the entire system, times the acceleration. If we wanted to actually get a number in here for this, we would have, oh, I'm going to have to insert some numbers for this force of friction. The mass of the entire system. But what about this force of friction? Well, let me move this up a little bit here so you can see it. That would be the normal force, mg sine of theta, m1 g sine of theta times the coefficient of kinetic friction plus and you really could just insert numbers if you wanted to make that a little easier. And that will give you the acceleration if there's friction on the incline. Hopefully that helped you create some formulas for these 3 different scenarios.